So for the second talk, here are the data. I assume I am giving t greater than 0, and the interval 0t will be time interval during which the game will be played. And I will be given beta naught, beta greater than or equal to 0. And the case beta naught equal to 0, beta equal to 0 will correspond to deterministic game, which means that I will be dealing with a PD which has no second order operator. I will be more specific. You will see precisely the PD in a few minutes. So I am given a Lagrangian. This is just a function on RD cross the set of probability measure on RD cross RD to R. I assume that this is a smooth function, which I refer to as a Lagrangian. And in the game, it represents the running course. So the first RD serves as a position. The last RD serves as the set of velocity. And the set of probability measure is the distribution of the players. So I will also assume that I am given a function g from RD cross the set of probability measure on RD into R. This is a smooth value function. Which represent the terminal value of the game. From the Lagrangian, I can define a Hamiltonian H of Q mu P. This is the supremum over V in RD. The inner product negative V P minus L of Q mu V. And you can recognize that here I am computing the Legendre transform. For Q and mu fixed, I am computing the Legendre transform at negative V because I am writing the inner product of negative V and P. So here is the setting. All players share the same common noise. So I am not telling you how they share the same common noise because I don't want to introduce the notion of a Brownian motion at this point. Otherwise, there is a Brownian motion W naught, which affects every player. The second assumption is each player has the same its own Brownian motion. Wi and W naught W1 to Wn are independent and identically distributed. So if you are not, in case you are not comfortable with data, you can ignore it because I am not going to use this directly in my computation. I will not try to derive the equation which appear in Millfield game. I am just going to write the equation and ask you to believe me that I am writing the correct equation. The value function of player I is ui from 0t cross rd to the n into r is to be found. So I am going later to write the equation which the value function will satisfy. But before I do so, I need some notation. The game is such that the velocity of player J is Vj. It depends on U, where I set U is U1 to Un. So it depends on the gradient of this function by the following expression. I compute the gradient with respect to P of H at Sj, 1 over n minus 1. The sum K is not J, delta Sk. And eventually I have the gradient with respect to the J variable of Ui. Actually, this is Uj, sorry. So from deriving the equation, one shows that finding a unique Nash equilibrium for the game is equivalent to solving the following system of PD. So you may either be interested in the game formulation, game aspect, but you may be interested on purely the PD aspect. I'm going to call it PD, depending on n variable. It will be the derivative with respect to time of Ui minus beta, the Laplacian with respect to all the variables of Ui minus beta naught. This will be an elliptic operator, which is degenerate. So you will compute the trace, the gradient with respect to Si, Sj, Sk of Ui plus H of Si, 1 divided by n minus 1. The sum J is not I, delta Sj, and gradient Sj of Ui plus the sum j from 1. J is not I, the velocity, j, u, gradient sj, ui, this inner product equal to 0 for I 1 to n, and the terminal condition G at time t ui at time t x equal to G of Si 1 over n minus 1. The sum K is not I, delta Sj. So let me comment a little bit on this equation and its difficulties. So here I need Sj, Sk. So this term, which look at first strange, it is obtained from the following. If you differentiate ui of t xi plus the velocity, if you differentiate that, you get dt of ui plus some mixed term, the sum j. And here, I am going to take all the velocity except the velocity of player I. Therefore, I am going to sum j is not equal to I, the gradient of Si, the inner product with the velocity. And this is what explains the presence of these two terms. So the derivative with respect to t and the mixed term, this is in fact a directional derivative. Now here are some difficulties. When you look here, and many other places, you see that I have 1 over n minus 1 instead of 1 over n. So if we could replace one over n minus 1, the sum j is not I, delta Sj, by 1 over n, the sum j from 1 to n, delta Sj, the system of PD will be easier. To solve. So one of the main difficulty in solving this system of PD is the appearance of 1 over n instead of 1 over n minus 1 instead of 1 over n. This is why when n equal to infinity, then there is no difference between 1 over n and 1 over n minus 1. The PD may become easier for an infinite number of players. So I am going to replace 1 over n minus 1 with some j is not I, delta Sj, by measure mu. And I am going to impose that this measure mu, if you apply it to a single a set with a single element, you get a 0, which means the measure mu has no atom. This is what makes it easier to solve a non-atomic game than solving a general game. PDN is not known to admit a unique solution. For a large time. The situation becomes even worse when both beta naught and beta are 0. So let us pass into Fourier transform to understand the role of this operator. So when I pass into Fourier transform, I have beta, the sum, psi I square, u hat, I. This is what corresponds to the Fourier transform of beta ui, the Laplacian of ui. And when I look at beta naught, the sum over jk, the trace gradient sk, sj of ui. In Fourier transform, this gives negative beta naught, the sum of psi k, psi j. So that operator is elliptic, not degenerate. This one is elliptic, degenerate. So if I look at just this and that. Therefore, beta is strictly greater than 0 is beta. That is better for the game with n player, but more importantly for the game of infinitely many players. This is why from the beginning, what has been well understood is the game with individual noise. So individual noise means beta greater than 0. Beta is the intensity of for the individual noise game, and beta naught is the intensity for the common noise game. So you can check that this is nothing but negative the sum psi j square. And you can see that the fact that this expression vanish does not imply that all the psi j vanish. So I want to move to the part with infinitely many players. So from now on, I want to focus on arbitrary many players. Which will include infinitely many players. So we need to understand what the limit when n goes to infinity, the sum I from 1 to n, the Laplacian with respect to Si mean, and the limit when n goes to infinity, the sum Jk, the trace gradient Sj, Sk. We need to understand this when n go to infinity. So this brings me to the following definition. This is what we term partial Laplacian. This terminology came from a joint work with Yatin Shao and myself. So let U be a function defined on Rd cross the set of probability measure on Rd into R. And I want to define the partial Laplacian of U. We lift U to obtain U hat from Rd cross H to R, where U, H equal to is the Hilbert space 0, 1 to the D, Rd, and that will be the Lebesgue measure on 0, 1 to the D. So in the first talk, I said that the set of probability measure can be viewed as a quotient space of that Hilbert space. And so when I have a function on the quotient space, I can lift it on the Hilbert space by setting U hat of Q. X will be U of Q, the law of X. Let E1 to ED be any orthonormal basis of Rd. In fact, I should have said these are constant vector field which are orthonormal on the Hilbert space. So I am looking at a very special vector field and set EI to be 1 over square root of 2 EI. So the first EI, I interpret that as an element of Rd, and the second one, I interpret that as an element of H. So to rewrite this, I am saying that this is in Rd cross H, where the second component is interpreted as a constant vector field. You can check that this is an orthonormal family. Of RD cross H with, you can guess the inner product on the product space. The partial trace of U hat with respect to the orthonormal family E1, ED is, I will use the following notation: U hat QX. This is the sum I from 1 to D. I am going to compute the Hessian of U hat at QX and apply them to the vector field. More precisely, you can check that another way of defining this is I differentiate twice with respect to time U hat of Q plus T over square root of 2 EI X plus T over square root of 2 EI, and I compute the second derivative at T equal to 0. So I take a second order Taylor expansion and keep the quadratic part, and this is the Laplacian, partial Laplacian with respect to an orthonormal family, which is far from being a base of the whole infinite dimensional space. So there is a result. Based on the result due to myself and Tudorescu, this function depends only this function can be factored. So you can write it the following way. You can write, the statement is this function can be factored as F composition X. And by definition, we call F the Wasserstein Laplacian with respect to E1 ET. One can also, instead of using this Hilbert space approach, one can also assume that U is sufficiently smooth. It admits a second order Taylor expansion in the set of probability measure. And when you write that second order Taylor expansion, you get the same definition of the Wasserstein, the partial Laplacian. Theorem. I am going to use the notation F is the Wasserstein Laplacian of U at Q mu. The first part is the Wasserstein Laplacian of U coincide with the common noise operator introduced by Lasry and Lyon in mean-field game. Second, I want to compute what the Wasserstein Laplacian is. Wasserstein Laplacian of U at Q mu equal to 1/2 the Laplacian, the finite dimensional Laplacian of U at Q mu plus 1/2 the integral over R to D, the trace. You compute the Wasserstein gradient twice of U at Q mu Q bar. Q tilde mu dq bar mu dq tilde plus 1/2 the integral over R to D it is not a mistake, but I didn't want to present it that way. I prefer doing the following. I prefer writing this. What I erase, I want to write it here, trace, and you will see why I want to write it here soon. So this will be the gradient with respect to Q, with respect to mu, of U, of T, of Q, mu, Q bar, mu, D, Q bar, plus eventually 1/2 the integral over R to D, the trace, the gradient with respect to Q bar mu, U of Q mu Q bar mu dq bar mu dq tilde. So I need to give you some explanation to understand this complicated term. But before, I wanted to group these two together because this is what is called the individual noise. Operator in mean-field game. So the individual noise operator can be obtained from the common noise operator. So the common noise operator is split into two parts. One part which produce regularity, which is the individual noise operator, and one part which destroy regularity, which is the common noise operator. So to see it from the Fourier transform point of view, when you write the sum jk, psi j, psi k, you can write it as the sum psi j square plus the sum j is not k, psi j, psi k. So this is going to produce regularity. This is going to destroy regularity. And this is how this represents the individual noise and the sum represents the common noise. But I also need to give you some information. Assume I have a function V from the set of probability measured on Rd to R. I define V hat to be V composition velour. I compute the gradient, Hilbert gradient of V hat at X. And we have a theorem saying that it can be factorized to obtain the Wasserstein gradient of V at mu composition X. So the Wasserstein gradient of V at mu is a vector field from Rd to Rd. And so for each Q bar, this will be an element of Rd. Now assume I take a function U which depends on Q and mu. When I compute the Wasserstein gradient, Q is fixed. I will differentiate with respect to mu. And for each Q bar, I'll have an element of Rd. This explains why here you have an extra argument because you differentiated once with respect to mu. Here, I have two arguments, Q bar and Q tilde, because I differentiated twice with respect to mu. You can also do all your computation in the Hilbert setting and try to interpret it in the set of measure if you are more comfortable with Hilbert setting formulation. So here is the master equation. One can show that there exists a unique Nash equilibrium in a game with arbitrarily many players represented by measure mu. This is equivalent to showing that the following admit a unique, the following PDE admits a unique smooth solution. So the PDE consists in find U from 0T cross RD cross the set of probability measure on RD into R, such that negative the derivative respect to time of U at the T Q mu plus the Hamiltonian at Q mu gradient Q U at T Q mu. So until now, I have written only classical objects minus beta, the individual noise operator U applied to T Q mu, where the individual noise operator is what I wrote here. Minus beta naught. The common noise operator plus, in the case with finitely many population, we have a directional derivative, which is given by the integral over RD. I am going to take the Wasserstein gradient of U at T Q mu Y. And I am going to write an inner product with a velocity, which depends on U, at the T Q mu Y dy equal to 0. And U at T Q mu equal to G at Q mu. So here, the velocity V of U is the gradient pH Y So I want to express this as a function of T Q mu Y mu gradient Q U of T Y mu and then here it will be Q. So this is the so-called master equation. In Millfield game. So I want to end stating the two existence results which are known for the master equation. Theorem A, this is due to Cardialaguet, Delarue, Lasry, and Lyon. Assume that H is separable, which means it can be written H naught of mu P minus F of Q mu. So assume you can separate the variable Q and the variable P. And H and G are Lasry Lyon monotone. I am going to come back to this definition. Then the master equation has a unique solution for large time. So assume that instead of giving Lasry Lyon monotonicity, there is a general definition for Lasry Lyon monotone. Better just to make a quicker point, assume that F is derived from a potential. Lasry Lyon monotone means that T goes to F of 1 minus T mu naught plus T mu 1 is convex. So Lasry Lyon monotone, in the case where the force F is derived from the potential, it is equivalent to convexity along traditional interpolation. Theorem B. This is due to myself, Bezaros, and Zhang. Assume H and G are displacement monotone. Not necessarily. Separable. So we introduce a concept of displacement monotonicity, which was inspired by optimal transportation theory. Then the master equation has a unique smooth solution for large time. And here too, I should say a unique smooth. So displacement monotonicity although the definition exists in general, let me give you it in an example. Assume that G is derived from a potential. Displacement monotonicity means if you differentiate, so set G hat to be the lift of G. If you differentiate the function T goes to G hat 1 minus T S naught plus T S1 is convex. So this is equivalent to say, so I want to compare Lasry Lyon to displacement using the same notation. T goes to G 1 minus T mu naught plus T mu 1 is convex, and displacement monotone will say T go to G of identity plus T. One minus T identity plus T X push forward mu naught is convex. When you try to use the displacement Lasry-Lyon monotonicity, when you try to do that and you give up the fact that the Hamiltonian is separable, it looks so far very challenging to prove, to solve the master equation, find smooth solution, or say if they are unique. I am going to stop here.